Hi, everyone. I'm happy to see that so many people are interested in large language models and research and everything. So today, I and Daria will tell you about our latest work in NVIDIA, our latest research. I'm working as applied research engineer at NVIDIA for 1.5 years. And Daria is right now an intern in applied research team at NVIDIA. And we will tell you today how to build an LLM for mass reasoning without use of proprietary data. Let's start. So first of all, I will do some introduction to what are large language models and what is mass reasoning. Then I will tell you about our research a little bit. And then Daria will tell you about tool that we used for searching for insights in data and some interesting insights that we found using the tool. Let's start. So what is large language models? I hope everybody here used ChatGPT at least once. And this is like a very good example of large language models. This is just, without going too deep, this is a neural network that predicts next word given some prefix. But how do we get this advanced neural network that predicts next word so well that like we can sometimes cannot distinguish it from human, sometimes it can do very hard tasks. So first of all, we need to prepare huge data corpus consisting of more than 1 trillion words. For latest Llama 3 model, it is 15 trillion of words. So basically the whole internet. Then engineers do some basic cleaning, remove duplicated data or data from some untrustful sources. And then we just take untrained neural network and pre-train it on this huge data corpus to predict the next word given some prefix. So we train the model for like 1 to 3 months to do this using a huge amounts of compute. Then we get pretty capable trained neural network that is already knows a lot about our world, that can, but it only can predict next word. It can't follow your requests. It can't, I don't know, summarize text that you ask it to summarize out of the box. So here goes the second stage called supervised fine-tuning. It is when model is trained to predict some response given some instruction. To do this, researchers basically collect some smaller, much smaller than the first one. Researchers collect a dataset that is much smaller than the first one, consisting of, let's say, hundreds or millions of pairs, instruction and response expected to the instruction. And then the model from the previous step is trained for another couple of days or weeks on this very high quality, small amount of curated data. And then we have a pretty capable model that already can follow your instructions. You can ask it to solve math problem or to write a letter. The next stage is chat fine-tuning, which is used to adapt model to act as a helpful assistant in the chat mode. But we will focus today on the second stage. And keep it in mind, please, that everything I and Daria are talking about is the supervised fine-tuning, when we already have some pretty capable base model, and we just train it to produce some solution based on the question. OK. Now let's discuss mass reasoning challenge. Basically, when the researchers publish a paper, or just publish a model without paper or whatever, they report some benchmark numbers to allow people, users, to know how good is their model. And models are pretty good at natural language understanding and natural language generation, like to summarize something or to write something simple, to rewrite something. Is quite easy task for a large language model, but reasoning is still challenging. So recently, a lot of effort of researchers was focused to improve reasoning abilities. And mass here is a very convenient way to measure such reasoning abilities. Because first of all, mass is easy to evaluate, because at the end of the problem, you almost always have an answer. So you can take the model-generated solution, take the answer that model produced, and compare it with ground truth answer, and you get the numbers. And the second, mathematical problems are reasoning problems, basically, because math, to solve the problem, requires some reasoning. You do some logical steps that goes one after another, and finally you get the answer. So that's why mass reasoning is quite an important problem, which everyone try to optimize their networks for. And everyone from OpenAI to Anthropic and Google and Meta report their numbers in mass reasoning because it is a proxy for general models' reasoning abilities. OK. Couple of words about datasets that we used for our research. There are a number of datasets. We focused on 2 for training and on more for evaluation, but this doesn't matter. So the first one is grade school math dataset, which consists of 7.5K training problems that are all basically looks like the one on the screen to the left. They are just math word problems that require 2 to 5 steps to solve them. And they always have integer solution. The second one is math, which is way more challenging. It is university level math problem collection, which also have 7.5K training samples, divided across 5 difficulty levels, 1 to 5, and 7 different mathematical topics like calculus, number theory, geometry, algebra, intermediate algebra, and some more. And the problems are, as you can see, much, much harder. So some of the problems, even I and my colleagues are unable to solve without hints from the dataset, at the first glance at least. So all these datasets, both of the datasets, have question field, answer field that is required to verify if the model produced correct answer, and solution field. So solution is basically a text-based, human-readable solution, regular one. But how can LLM solve the math problem? We have the first one is text-based solution, which is what we expect as a humans to get. So if you don't see exact solutions, this doesn't really matter. The fact is that text-based solution is just a regular text solution to a problem that we all write at school. But for large language models, it have some disadvantages because LLMs are quite bad at arithmetic. And this harm performance sometimes pretty much. And this is not really related to the reasoning because like the reasoning could be correct and the model can still do some arithmetic mistakes and we get incorrect answer. And then we can't clearly assess model's performance. So here comes the second solution style, that is code-based solution, where we ask model to write a code basically in any language. Python is used because it is most popular across the internet and very simple. So now model still needs all the reasoning. It needs to define all the variables. It needs to make solution flow to perform some iterations. But all the arithmetic now is performed inside Python, and model don't need to like think about it too much. But this method also has some problems because it is, first of all, it is not what we will do as a human with a calculator tool. So here goes the third way, is code interpreter. So at the beginning, so code interpreter is basically when model can both write text and call code tools whenever it's needed. And it is the most natural way of solving problems for a human with a calculator. You will write some mathematical model, you will perform some modeling, then you will transfer all the calculations to the calculator and just calculate the final answer. And it is more general as well because model can write some text, then write some code, then post-process the answer, then give the answer. In our work, we use this style, code interpreter style solutions like this. So given question, model writes some solution in text. Let's solve this problem using Python code. Then it writes special LLM code tag and writes Python code. When it closes LLM code tag, we take all the generated code and execute it. Then we append result of code execution back to the model, and model continues its generation. And model is able to see the answer code returned to the model. Now we can continue to our work. So all the prerequisites are satisfied. So what we have done, we created 1.8 million instruction tuning dataset with GSM 8K and math questions and our synthetic solutions. We trained models on this dataset, a number of models, Mistral, Llama 2, and Code Llama 2 families. And we release everything, so models, dataset, and code under open source licenses. Some results. On the top, you can see 4 entries, which are some competing models. All the 5 models in this table are based on Llama 2 70B. And as you can see, some of the models are not using code, so they just perform reasoning in plain text. Some of the models use code as well as we. But all the models above use commercial, non-commercial OpenAI data, because according to OpenAI terms of usage, you cannot use their data to train models and gain profit after that. And we don't use any OpenAI data for our model training, and still get pretty compatible results. So on GSM 8K, we outperform all the models above, or gets very comparable results. On mass, we a little bit behind the best model, but all of this without using any commercial data and spending money on the API, only on the compute. But GPT-4 is still way ahead of any models based on open source. So as you can see, when GPT-4 is using code, it gets like 12% more on GSM 8K97, almost like solved the benchmark, and 70% on the mass, which is also pretty impressive. And I think latest models of GPT-4 are even better in mass using code. So let's discuss our pipeline to get such results without using GPT-4, and what do we even do to create dataset? Why 1.10 million when we have only 15K combined questions? So first of all, we need a training dataset to be labeled. We have, as I have already told you, question, answer to compare with, and solution, which is not really required in most of our pipeline, but sometimes it could be useful. I will tell you later why. Base model basically is any large language model you like. For us, it was Mixtral model, which was the strongest model up to date. But right now, obviously you can use any other model. You can use even API model, but yeah, then you have problems with data license. And the more capable is labeling model, the better results you will get. And a few short demonstrations. These are used to provide model with format we expect from it to create solutions. So we can tell model just solve the following problem, but most likely it won't follow the required solution format, because here we have things that model wasn't trained to produce, like LLM code start, LLM code finish, LLM code output. And to fix this, we write basically a few short demonstrations for each dataset that includes one training question and one solution to this question, and 5 times this. Then we take these 5 examples, concatenate them into the whole prompt, and put these 5 examples into our model and ask model to label the new question from the training dataset. So here is how we synthesize the whole data. We generate n solutions per problem. N is like 128 or 256, or even more for harder problems. Then we take the answers that produced by the solutions and remove all the problems with incorrect answers. Like, we don't want to see solutions that led to incorrect answers in our training set. So this is a very simple way to get pretty good and huge data set just using brute force scaling of generation. Then we perform some basic filtering and remove some obvious stupid solutions. For example, the ones who get the right answer by chance, like if solution is very short or solution contains multiple answers or something like this. And then we just have a pretty good synthetic dataset, and we take some base model and fine-tune it. But we have another problem. As I already told you, GPT-4 is way stronger on GSM and on mass datasets, so it is stronger in generation the synthetic dataset. And this is why everyone is using GPT-4 for creating their synthetic datasets and getting pretty good results with this. And here is what we get if we compare Mixtral with GPT-4 models. So on the y-axis, we see training set coverage in percent. It is how many problems are solved using a set of our solutions. And on the x-axis, we see a number of samples per problem. So, for example, for GPT-4, we have constant lines at k equals 11 number of samples per problem. And the problem, this means that the problem has 11 solutions generated by GPT-4. And the problem is counted as covered if at least one of the solutions leads to the correct answer. So as you can see from this plot, too much GPT-4 coverage at just 11 samples per problem, Mixtral model needs around 100 solutions on GSM 8K. And on mass, we cannot even match GPT-4 with 128 solutions per problem. And this is bad, because to have good dataset, to obtain good models after fine-tuning on this dataset, we need diversity in data, and obviously we can't add problems to our dataset that are not covered by our synthetic solutions. So we suggest the following method. We remember that mass dataset. So for GSM, this is not a problem, because for GSM we have basically 100% coverage. But for mass, this is crucial. So we suggest the following simple method. We remember that mass dataset contained ground truth reference solutions to the problems. They are not that good to fine-tune on them, but they can be leveraged as a hint to the model on generation, on synthesizing labeling stage. So what we do here is just provide not only question and few short demonstrations, but also providing a reference solution. And here what we can get from this method. You can see that model just uses the final answer. So the model take hint not really seriously and just hacked, cheated, and took the final answer and presented it as the answer the model came up with. Obviously, we do not want to see such solutions in our training dataset, because the solution do not provide any useful information to our training. The model just takes some number as an answer and output it. But we still need to use a hint somehow to increase our coverage. So here comes an interesting method that we came up to. As you can see, here we have ground truth text solution, which is solution mass dataset have. And we replace all the intermediate computations by some letter variable. So large language model now cannot take some intermediate computation or the final answer and use it in its solution. But we still make a very valuable hint to the model of how we want it to reason. So the solution still provides correct reasoning, but model can no longer provide cheating solutions. And this simple trick helped us to improve training set coverage by 13%. While having very clean data, without any cheating solutions and without requiring us to spend a ton of time to filter such cheating solutions. So this is it for my part. The questions will be in the end. Right now, Daria will present her part of presentation, the tool, and some interesting insights.
Hi, everyone. My name is Daria, and I'm going to tell you about the Data Explorer tool that we've created to help us with our work. So we will start with the introduction to the tool. It will include the reason why we created it, why we didn't just use some existing tools, and what's the key feature of this specific tool. And then we will see the tool itself. We will try to make some analysis on our data. It will not cover all the features that the Data Explorer has. So if you will want to know more, you can follow the QR codes. And here you will find the demos, the full demos of each page of the Data Explorer tool. OK. Let's start with the introduction. Let me quickly remind the model development loop. So first of all, we'll need to have a model and a dataset. The bigger the dataset and the better the quality of the dataset, the better results we can have by fine-tuning the model. So then the next stage is fine-tuning the model. And after the model is ready, we need to use another dataset, which was not used in the fine-tuning stage, to check the quality of the model, how well it works. So then, after we get the results, the generations from the model, we should check it. We should try to find some common mistakes that model produces, or maybe we will find some more mistakes in the dataset, and then go back, clean the dataset, change something in our setup, and so on. That's the model development loop. The tools that we are presenting today will focus only on the inference stage and on the analysis of datasets. So everything else is not included in the tool. It's not our focus. Let's talk about the tool. So there are two types of tools for data analysis. The tools for general data analysis and tools for LLM-specific data analysis. With this it's not working. OK. With this red-orange line, I will mark this feature which tools for general data analysis also has. And with the blue one, we will mark the feature that tools for LLM-specific analysis will have. So speaking about the Data Explorer tool, what we written down as a key feature that we want to implement and later use. So first of all, it should have the streamlined inference through entry points on the whole dataset and on the single question. So we can do the inference on the whole dataset, and we can check some hypotheses on a single question. Why through entry points? Because we are working with large models that are located on our clusters, and we don't really want to move them around. So the inference should work through entry points. By streamlined, I mean that we do not need to write some scripts or Python code in order to do the inference. So it's just a single button click, and you'll get the inference. I have marked the inference word here because tools for general data analysis also has the ability for inference. But in order to do this in these tools, you will need to write some Python scripting. We want to have interactive changes in parameters. What do I mean by this? That if we change some settings, if we change some prompts, templates that we use to combine the whole prompt, or if we change a few shorts, I want to see them. I want to see the whole prompt changes. So I want it to be visualized well, so I can generally see what was changed. And I need a markdown LaTeX in Python syntax highlights and support. This one is specific for the mass dataset, we are working with math, we are working with LaTeX formulas, and we are working with Python. So we need to visualize well. And later we will see why the LaTeX formatting is so important. During the demo, we will not cover this ability of the tool. We will not do inference. So I have added screenshots on the slide. It is probably not really clear, but OK. So we have the run one sample mode, when you can send a single question to the model and get responses. It will be validated, and all formulas will be rendered. And we have run whole dataset mode, when we do the inference on the whole dataset. And then the model will produce us with statistics only, and it will write down the pathway we can find the generation. The analyze page, the data processing part, we also need the good visualization of our samples. So we do need the Markdown, LaTeX, and PyData syntaxis highlighting. And we do not want to scroll to see the whole sample. So tools for general data analysis, they use a table-like visualization, like Excel or SQL tables. So in order to see the whole sample, you need to scroll. Here we try to pack the whole samples in the blocks, so we don't need really the scrolling. We do need statistics, sorting, and filtering. All tools for data analysis has it. It's an essential part. But here we want to make them custom. So we want to write our own functions to filter, sort, or make statistics. Labeling, all tools has as well, and we think it's essential. So in our tool, there is also such option. And the Data Explorer tool also has a prepare workflow for the LLM-specific analysis. So we'll talk about it later as well when we will move to the tool itself. So generally, the tool just understands some entities that are specific for the LLM analysis. Here's a comparison of the visualization in one tool for general data analysis and Data Explorer tool. You don't probably see it well, but believe me, on the left side it's hard to read because there are large LaTeX formulas, which without proper rendering, it's hard to understand. And on the right side, we have the visualization of the Data Explorer tool with good rendering of LaTeX formulas. Here's the important links that you can follow. The link to the NEMA skills repository, the link to our paper, the link to the tool, and to the tutorials that you can watch if you want to know more. I will back to the slide when we will move to the questions part, but for now, let me move to the tool itself. First of all, we will need to choose the base generations that we want to analyze. Here I have two generations. They were produced by Mixtral model, and it is early versions of our datasets. It's pre-list versions and pre-list early versions of our datasets. So we have here the masked generations with the annotations that Ivan told you about, and without the annotation. So let's choose the masked generations. When we choose the base generations that we want to analyze, we can see the table with each question and some statistics that are counted. Let's see what does the statistics mean. So here, we also have a list of generations for each question. What is the difference between these generations and the generations that we've chosen here? Here, basically, this is, roughly speaking, we can say that these generations are generations with different setup. But the meaning of it is that we can't combine these generations. They are so different that the statistics that would be counted through all two generations would not have any meaning for us. So yeah, we can only compare the generations and just like see them together. And these generations, we can count the statistics for each question. And in our specific case, these are the different random seeds for each question. So these are pretty like similar generations which we can combine and work as it is a one entity. Okay, let's talk about the dataset as well. Not this one. Here. Can I a bit, is it still visible? I make it a bit smaller. Okay, we have 2 code blocks here. We can turn on the syntax support, and we will see the same thing that I showed you. We have LLM code tags, we have LLM code output tags, and we have the boxed field. So the predicted answer field was taken from the boxed field. If you do not have this thing in our generated solution, we will not have the predicted answer field. It will be none. Okay, that's everything that we need to know about the data before the analysis. Now let's start to do some analysis. First of all, let me sort the data. So I want to have, at the first I want to see the lowest correct responses number. So I want to see the hardest sample in the dataset for the specific model. Here's the AM. So let's take a look at the first question. What we can see here, that we indeed do not have the predicted answer field. It is none. Why is it so? Because we do not have the boxed field in our generated solution. This happened because the code that the model wrote was executed with an error message. And then the generation was stopped because of the error. We had quite a lot of samples in our dataset with this error, so we tried to handle this issue. And I will not tell you about how we handle it, because it is going to be released in our new paper. By handling these issues, we could improve the results on the mass dataset by 2%. Okay, let's switch to another random seed. Here, we also have an error message, but it doesn't actually show us an error. It just indicates that the generated solution doesn't have a code block. So if you don't have a code block, we will have this error message that stated not executed if you don't see. So let me extract all the questions with text-only solutions. Here's I am. Okay. Yeah, I had an error in filtering, so now it should work. So here's I am. Let's take a look. So now what we are seeing here, that the reasoning was correct of the model, and this actually expression is right. So if we solve it, we will get the 11th, 15th, the fractions that we expect the model to answer. But the model just couldn't do the arithmetic correctly, and it fails to produce the correct response. So we have such cases. And by handling this specific issue with poor arithmetic ability, we could improve our results on GSA-made-cut dataset on about 4%. Okay, now I want to show you one more issue with the dataset. I have prepared a specific filter for this. What samples we will extract here? We will extract samples where we mark the samples as incorrect, but we will extract the value from the last code output block, and we'll compare it to the expected answer field. If it's correct, we will consider that it might have the right reasoning. but something was wrong after that. So in the boxed field, we have the wrong answer because the solution is marked as incorrect. So let's look on such samples. Okay, what we see here that the answer of the model is exactly the same as the expected answer field, but in the boxed field, we have written some additional information. We have written 49 feet. And because of that, we couldn't really evaluate the results correctly. So we marked it as incorrect, but it is actually should be correct. Let's see another one. It will be the last one that we'll see. Here, a bit different issue. We also have the right reasoning. And we could produce the correct answer. So it is the expected answer field, the same number as the expected answer field. But the number in box is different. Why is it so? I have seen many cases when the number in boxed field was just some random number, but this one is not the case. Here, it took the number from here, from the beginning of the reasoning. So it performs the same multiplication, the same expression by itself, failed in arithmetic, produces their own answer. Then the model did the same in the code, produces the correct answer, but in the boxed field, it was still incorrect. So what I wanted to tell about by showing this example, these last two examples, that not always when we mark the samples as incorrect, it is actually wrong. So we can just fail in evaluation. It was pretty much everything about the tools demo. It has many other features. For example, we can compare models like this. We will not go further for any more options that we have in the Data Explorer tool. If you want to know more, the QR codes are for you. Great, thank you. Now we can move to the questions part.
Thank you.
Okay, so if I correctly understood, did you use synthetic data for training? Am I right?
Yes. So
okay, but how exactly you generate correct synthetic data? Still not clear for me.
Okay. We get the dataset, GSM-8K and mass.
Which dataset? Mass
and GSM-8K.
Okay,
they combined have 15
This dataset
right?
contains dataset and some benchmark questions which
they
selected from dataset.
Training part and holdout test part. We report the numbers on holdout part and training.
How many questions and answers? How many examples in each dataset?
So the original datasets themselves have 7.5K questions in the training part and like 1K for GSM in test part and 5K for mass in test part. But we, for training, we use question from the training part of these datasets and create a lot of solutions per each question using these few short demonstrations.
But actually, a lot of solution, it not means you have a lot of different answers for the question.
Yes, of course, we make deduplication, so solutions are at least somewhat different between each other. And if I understand you correctly, like you ask about diversity of the synthetic dataset we get, right?
Yes, we get diversity, but we don't. How we label data as this generated solution for synthetic data is correct, and how you check generated examples?
So yes, this is for each of the training problems we have correct answer, right?
Yes.
So when model generates a solution, the solution ends with the answer as well. So we just take the model-generated answer and the ground truth answer and compare them. And we leave only correct solutions, and they form 1.10 million datasets.
Okay, and solution is just a Python code?
Not only Python code. It is some natural text with Python code blocks. Yes, LaTeX solutions.
Okay. LaTeX solutions and Python code solutions.
Yes, and model can call Python code blocks multiple times.
Okay, and you use code interpreter to execute this solution and compare.
And can continue generation, right?
Okay.
As I see, you expect 3 answers for a question in the result. Did you try to get them one by one? For example, the first try is a text answer, then ask to generate the code, and then the third task is to extract the solution instead of asking for the full result in one response.
So, do you mean break the problem into steps?
Yeah, into steps and ask step by step. So the first one is the text representation, then the code, and then the extracting from the code. I think this will be much easier for LLM to understand what you want from it.
So we tried all these 3 approaches separately, and the last one worked best. But I think we're already doing what you're suggesting, because in few short examples, we have both only text and only code examples. And also we have examples where we have a long text reasoning at first, when model can build some mathematical model. And then we show how to write Python code that executes this mathematical model and gets the final answer. Did I understand your question correctly?
Probably yes. So as I saw, the model can produce errors just by extracting the wrong answer at the last step. So if you train, for example, in 3 steps at the first, the combined one, maybe it will be a better result.
Yes, we did not try that, but this might be a good idea. And for the error of extraction answer, it was more like some interesting example of what model can generate. This obviously happened because we use random sampling to generate diverse set of solutions, and because of high sampling temperature, the model can produce quite different trajectories. And we just looked at some extreme example of how wrong model could be. But actually, the model is pretty good at writing consistent solution from start to the end and extracting code answers. Yeah.
So just a small amount of errors, for example, not often.
So we have a lot of errors, but they are very different. And most of them are not connected with extraction errors. They are more like some problems with reasoning when model unable to understand the problem correctly or just don't know how to solve very hard mathematical problem.
Yeah, thank you.
Thank you.
I was actually going to follow up on that gentleman's question. Can you walk through just a little more step by step how the code, like what's actually going on behind the scenes with the code interpreter solutions? Like, is there a system that's parsing the style solution and executing it? Like what does that architecture look like?
Okay, so you mean what's our software implementation of this code interpreter style? Okay, it's not that hard. Basically, all we need is to provide close LLM code tag as a stop word for LLM. So it will stop generating the sequence after generating LLM code closing tag. Then we take the code solution, which is like all the model generated up to the past LLM code starting tag. And we pass this Python code into our sandbox. And the most tricky part here is the sandbox, because LLM, because of a lot of randomness and huge number of generations, LLM can potentially produce very arbitrary, potentially harmful code. So we need to use very isolated sandbox that will not allow model to delete some files on our servers. But when we implemented such sandbox, we just send the code to sandbox. Sandbox executes the Python code and returns the result. So then we like surround the result with code output text and show it back to the model. So here is a large space for optimizations. For example, in our work, for simplicity, we do not recalculate KV cache on the fly, but we just start a new generation from scratch, but with the whole prefix. So model needs to we need to calculate KV cache like from scratch. But obviously, if you want to optimize, you can reuse previous KV cache. We just did not have much time to do this.
Just to be clear, is this an agent running behind the scenes doing all those steps, or is it just a pipeline that you have that sequentially executes each of those steps? Like, it's just not clear to me what's running these things.
So
that one after
the whole thing is LLM writing at first text. So this is LLM prompted with some demonstrations, with few shots, to write solutions in such style. The LLM at first writes this start text, then LLM decides to make all the calculations in Python and writes LLM code opening tag and writes the whole Python code and closes the tag. Then we stop the generation, extract the Python code, execute it in our sandbox, and give the result back to the model. Okay? And the very same model that is just LLM prompted with a specific way continues generation, knowing already the code execution answer. So for this example, this is like the model even wasn't trained for this. This is an example of solution that model can produce using few short examples. Okay? Yeah, thank you.
Thank you very much for the talk. Sorry, I missed first half of your talk, so maybe my question is stupid, and maybe it's a continuation of previous questions. So when you mentioned when it fails, right? So sometimes it's problem with like Python code, right? And sometimes it's just a wrong, let's say that's word feed after the number, and that's why it's. So do you consider some techniques on inference time, let's say, to add reflection when Python code fails, like try to regenerate it correctly, or maybe add structured output for extractor for this boxed answer? Yeah, maybe you already mentioned that, so sorry if
No, we did not mention this, and this is a great question. So the code recovery is a pretty useful technique, and other paper that is Tora 1 uses code recovery. They train their model to recover from code errors. Like we, for example, stop the generation when model produces failed Python code. But Tora trained model to recover from such errors. And in our paper, this was not our scope, but after that we tried this, and this gave us 2% more on mass, because yeah, so we basically regenerate the failed code a couple of times and do majority voting, and this improves the scores quite a bit.
Especially if you could add, let's say, error message, right?
Yes. And as for self-reflect, we do not use this, but we use chain of thought prompting, obviously, to make model produce more detailed mathematical models before writing code. And we also use quite extensive mass grader that you can find in our repo, which can handle a lot of differences in formats. So, for example, the example Daria showed you with feed prefix, actually in our latest code will be graded as correct, because we just make some more robust comparison of two answers. I mean. Thank you.
Thanks for the nice talk. I have a very general question, maybe silly question. In all good times, we were computing and developing algorithms which are tailored for computing. So because you are NVIDIA guys, and NVIDIA is the accelerator company, so my question is related to this general aspect. So you guys accelerate whatever is given to you, right? Now you reformulate the question, can you develop methods which are accelerating as well? So your performance might be not as good as GPT-4, for example, but then you can deliver the answer in like 10 times faster, right? So not only by accelerating using GPUs, but accelerating using some algorithmic methods. Did you thought about this?
This is another great question. So, yeah, in this work, we were focusing not on accelerating things, but in obtaining as high results as possible given a lot of compute. So I think optimization first is not the most clever approach in the problem solving. So at first you need to get a good performance in terms of I don't know, numbers on benchmarks, and then you can optimize this in terms of like production, inference, latency, and everything. So in this paper, we optimized. We were focused on optimizing the numbers, but yeah, optimizing inference is also an interesting topic, which I think we're going to explore maybe this year. Thank you.
Have another question about using LLM. So you use LLM that mostly optimized for text generation, but asked it to solve mathematical questions. So maybe you can get better results by relearning the empty neural network for math, for example, by only math articles and math examples, and then try to do the same with it instead of the pre-learned LLM. Did you try this?
No, we did not, but I think somebody tried something like this before. But the goal is finally to get a general assistant which is capable of like writing some letters and both solving some tricky reasoning problems. As I told before, reasoning is not like self-goal, but it is part of assessing the general model capabilities. But just we focused on the narrow part to how to take some general model and train it to reason well. So in your approach, I'm not sure if I remember any papers that train models on math-only things, but I guess the math performance of general trained models should not be way behind performance of model that was pre-trained specifically for math, because like I think the latest models also are heavily pre-trained on math data, and there is a huge amount of archive papers, of some Stack Overflow, of code data from GitHub that is used for pre-training. So I think starting from such general models and fine-tuning them on math data is good enough.
Yeah, but maybe they have a lot of math data, but the the percent of this math data is not so large. So when you fine tune it, the weight of such data is not high. So maybe you can create a LLM which asks another LLM to resolve some math problem and include it into the answer instead of trying to fine tune the larger LLM where the math is only the small part.
This actually is a great path for to be researched, to have a separate LLM that is trained on heavily math data only without general tasks, and our agent not calling Python but calling this math trained LLM. We did not consider this, but this is an interesting thing. Yeah.
Yeah, will be good to hear the results. Thanks.
Okay.
More questions? Thank you.